So it's almost time. Let's start. Good evening, Professor Jain, and good morning, Professor Wei, Professor Wang, Professor Liu, Professor Zhang, Professor Xu, and Professor Chen. Okay, I'm P. from the Department of Computer Science, Hong Kong Baptist University. I'm very delighted to welcome all of you to join the Honorary Doctorate Distinguished Lecture to be presented by Professor Anil Jain on fingerprint recognition. So today's lecture will last for around 1 hour, followed by 15 minutes Q&A, and then we will have a group photo taking. So before we start, I'm honored to invite Professor Alex White, the President and Vice Chancellor of Hong Kong Baptist University, to give the welcoming speech. Ladies and gentlemen, please join me to welcome Professor White.
Professor Jain, distinguished guests, fellow students, colleagues, and alumni. Good morning. It's my great honor to extend the heartiest welcome to Professor Anil Jain, a world-leading computer scientist to Hong Kong Baptist University, for this very special online distinguished lecture. Honoring his outstanding achievements in the advancement of science and technology in areas like AI and pattern recognitions, as well as their impacts to the society, HKBU conferred an honorary doctoral degree to Professor Jain earlier this month. It's such a privilege to have Professor Jain here with us today. Professor Jain received his bachelor degree in electrical engineering from the prestigious Indian Institute of Technology, Kanpur, and his master and PhD degrees from the Ohio State University. He is currently a University Distinguished Professor at Michigan State University, where he has worked for over 48 years. Professor Jain's groundbreaking contributions in technology advancement create a huge impact to our daily life. He conducts research in the areas of biometrics, pattern recognitions, machine learning, computer vision, and image processing. He led a team of computer scientists that successfully developed the world's first ever 3D fingerprint technology called Phantom. The breakthrough has hugely boosted the accuracy of fingerprint recognition systems and improved security technology. Professor Jain is active in technology transfer, for which he was elected to the U.S. National Academy of Inventors. He holds 6 U.S. patents on fingerprint recognitions and 2 Korean patents on surveillance. Research he has undertaken has led to technologies for fingerprint recognitions, tattoo image matching, facial sketch to photo matching, unconstrained face recognitions, and fingerprint obfuscation that have been licensed to IBM, Morpho, and NEC. Next time, when we unlock our smartphones or pass through immigration checkpoints, we should thank Professor Jain for his work, which creates the convenience to us. What's more, Professor Jain has made significant strides in academic impact. He's continually ranked #1 in the world in computer science and electronics, according to Guide to Research. He has been granted many honors and awards, including the Guggenheim, Humboldt, and Fulbright Fellowships, and IAPR Kingston Full Prize in 2008. He's a co-author of the Handbook of Fingerprint Recognitions, published by Springer in the 2003, 2009, and 2022 editions. Professor Jain was also elected to the U.S. National Academy of Engineering and Indian National Academy of Engineering in 2016, Chinese Academy of Sciences, and the World Academy of Sciences, both in 2019. Today, Professor Jain will take us on a journey of discovering fingerprint recognitions. Fingerprints are a unique feature comprising of rich wily pattern that everyone has. Fingerprint biometrics is widely applicable to every aspect of our daily life. Despite this giant leap, there are inevitably pressing and challenging issues pertaining to fingerprints. So Prof. Jain will share with us how new machine learning and artificial intelligence models are being used to address some of these challenges and to push the state of the art in fingerprint recognition. Prof. Jain, please accept our most sincere thanks for your valuable lecture. We're all ears and look forward to being enlightened by your keen scientific insights. Ladies and gentlemen, please join me to welcome our distinguished speaker, Professor Anil Jain.
Thank you very much, Professor White, for the welcome speech. Without further ado, may I invite Professor Anil Jain to give the distinguished lecture on fingerprint recognition. We are sharing the screen for you.
Thank you. Let's see, I need to go
I can start from the first page.
to the first one. I don't have the control yet. Okay.
Do you have the control now?
Not yet. I cannot make it full screen yet.
Yeah, let me.
Can you control the screen now?
Yes.
Okay, great.
Well,
Yeah, please.
good morning, everyone. It's a great honor for me to be awarded honorary doctorate from Hong Kong Baptist University, where I have visited a number of times. And I have collaborated with Professor P.C. Yuen on face recognition, and we even had a joint RGC grant together. In my 50 years of academia, about 30 years I have devoted significantly to fingerprint recognition. And it is not something which I had planned. In around 1990, I was in my office. It was sort of pre-internet days, and I received a call from Washington, D.C. And the caller said that, you have done good work in image processing. We will give you some new computer technology boards called FPGA, Field Programmable Gate Array, which attached to a Sun workstation. And they asked me if I would find some civilian applications of it, because that technology was developed for the National Security Agency. And they decided to send us the board and gave us a substantial amount of money and gave us complete freedom, find some civilian application of this FPGA technology. And one of the topics which we decided to pursue was point matching and image filtering. And these are pretty generic operations. But when we thought about doing point matching, which is often done in stereo and motion correspondence and computer vision, then the question came up, where should we get these points for some application? And that's where one of my students said, how about fingerprints? Because if you look at any crime scene, crime show, TV shows, you will see that fingerprint matching is done based on the points. So that's how our journey into fingerprint started about 30 years ago. And over the years, I think my students and postdocs have made a significant contribution to fingerprint technology. And despite the comments often made by computer vision and AI researchers that, oh, fingerprint recognition is a solved problem because it has been around for 40 years or so, we find that we can continue to find new problems, make new contributions, and do the technology transfer as well as publish in high quality venues. So I will go ahead and give you our contributions to fingerprints, how we got started. And I still don't have the control. So if you can go to the next slide, please. Yes. So there are three things I would like to talk to you: why we need fingerprint recognition, how fingerprint recognition works, and what's next. I still clearly remember, next slide. I was in Hong Kong when the first smart cards were issued in 2003. And prior to 2003, there were signs all over Hong Kong. And I was staying in a hotel in TST. And there were signs everywhere, go to this place, indicating where you can go and get your fingerprints taken to have the smart card issued to you. So I went to the, and the reason I'm showing this slide is because everybody who is in Hong Kong knows about fingerprints, because the smart cards they carry has their two thumbprints. So the first ID cards which were issued in Hong Kong were in 1949. Before that, it was not required for Hong Kong residents to have any identity card, and there were paper identity cards. Then came the laminated identity cards, which had one fingerprint in it. And then the smart identity card 2003. And now Hong Kong is going through this exercise of reissuing the smart identity card with new smart identity card. And why do they need a new smart identity card? Because it has better security features. So this clearly explains why we need biometrics or fingerprints in smart ID cards. Paper ID cards can be stolen or forged. Smart ID cards with stored fingerprints are more secure. They are very difficult to tamper. And that's the reason why everybody in Hong Kong is required to have these smart identity cards. It makes life convenience. This is not just only for security. You can go through the e-channels at the airport. You can get your benefits and many other things which makes it life easier. You can do electronic transactions and so on. Next slide, please. The other reason I want to talk to you about biometrics and fingerprints in particular is because everybody is familiar with it. In 2013, Apple introduced the iPhone with the finger touch ID, whereby simply touching one of your fingers at the home button, you could unlock the phone, and later the payment can also be done using the fingerprints. So if you look at this statistics, about 1.5 billion mobile phones were shipped in 2021 alone, and 1 billion of them have fingerprints. About 60% of the phones have fingerprint scanner in it. And this essentially shows what the huge market is for fingerprint technology. And people now take it for granted because the technology works. Nobody has complained about the fingerprint since Apple introduced the Touch ID. And the fact that so many people are voluntarily using fingerprints to unlock their phones and for mobile payments, it shows that there is a great acceptance for this technology. So you would think that, well, the problem is solved, what is left to do? And that's what I would like to emphasize. Next slide, please. If you look at human body, I think a substantial part of the body is covered with skin, which has hair on it. But there are three portions of the body, your palm and the bottom of your feet, where the skin is very different from rest of the body. And the palm print, the fingerprint, and the footprint, these all have what has been referred to as the friction ridge patterns. These are the ridges and valleys, which are, in a sense, perforated. And sometimes people wonder, why do we have these friction ridge patterns? Well, one common explanation could be that it allows you to hold some objects without slipping. So for example, just imagine a bottle of cold beer. If you want to hold it, what would happen if you didn't have the friction ridges? And so there's a scientific field called dermatoglyphics, where derma means skin and glyphics means carving. So this is the carving on the skin. And this has led to what has been referred to as palm print recognition, fingerprint recognition, and footprint recognition. While footprint recognition is not very practical because you don't want to take your socks off and shoes off to get yourself recognized. But for the newborns, it's a common practice, at least in the United States, to have a footprint of the baby. Nobody uses it for matching. It's just a souvenir for a newborn child. But fingerprint recognition and palm print recognitions are now prominently used in recognition. Next slide, please. So now I'm going to talk about fingerprints. And these are the ridges and valley pattern on your fingertip. And if you look at, just compare it to the size of a United States postage stamp, this is a small area, less than an inch by an inch, or about 2 centimeter by 2 centimeter. And it's amazing that this small skin on your whole body can be used to recognize who you are. That's the amazing, and this is a non-invasive procedure. I mean, one could say, well, I can use DNA to recognize you, but DNA capture and processing is not real time and it is invasive. So now I'm going to mostly talk about fingerprint recognition. Next slide, please. So even a newborn has fingerprints. This was, we have been working to sort of come up with a method to recognize infants and toddlers. And people tend to believe that, oh, before 2 years, fingerprints are not formed. And during our research, we have shown this to be false. Actually, fingerprint formation starts during the 10th week of gestation. It has both phenotype and genotype characteristics. So siblings may have similar looking fingerprints, but they still, because of the phenotype characteristics, they can still be distinguished. So identical twins will have distinct fingerprints. So this is the fingerprint of a 6-hour-old baby, which we captured in a maternity hospital. And this required a very high resolution, about 2000 PPI fingerprint reader. The matching of a newborn fingerprint is more challenging because the skin is soft and malleable. And so there's a lot of deformation which happens. And so we have not been able to successfully match 6-year-old baby's fingerprints a day later. So the earliest age at which we can recognize a child is about 3 months. But that's an area where we have been investigating, because in many of the least developed countries, there's a need to have an infant identification system to ensure that they are getting the proper nutrition and they are getting the proper vaccination at the right time. Next slide. So there are a number of properties of fingerprints which have motivated people to use fingerprints in a variety of applications. Each finger has unique ridge characteristics. Even all 10 fingers of your 2 hands are different in terms of ridge characteristics. So this is like a fusion problem. I can recognize you based on 1 finger, but if that finger skin is dirty, I can combine all 10 fingerprints to get a higher recognition accuracy. In fact, in forensics and law enforcement, they use all 10 fingerprints. These rich details are permanent. That means they do not change their characteristics sufficiently to pose a hurdle in recognition. So I can recognize, if I capture your fingerprint now, 20 years later, I can still recognize you. Identical twins have different fingerprints, and fingerprint evidence is accepted in courts of law. In fact, last month I was in India, and I had to go to the court for some family matters for land transfer. And in the court, they take your thumbprint that is still considered a legal signature, even though they never do any matching. But you have to go through the procedure of providing your thumbprint on the title of the property to be considered valid. Next slide. And most importantly, fingerprint evidence is accepted in courts of law. So that means if you make an arrest and the forensic expert says, yes, at the crime scene, the fingerprint left at the crime scene matches a suspect's fingerprints in the database, that means it's the same person. Next slide, please. So the earliest application of forensic fingerprints has been in the forensics and law enforcement. So there are two applications where all law enforcement agencies around the world are using fingerprints for. One is to identify repeat offenders. If one person is arrested, then their 10 prints are taken. So there's a standard for fingerprint where an officer will hold each finger and obtain what is referred to as the rolled prints. So then the left figure, the first two rows are showing the 5 fingers of one hand, 5 fingers of the other hand. And in the last row of the left figure, we have what is called the slap fingerprints, which have become very popular, especially for immigration and purposes, because you don't want to have somebody holding your thumb and capturing your rolled prints. So the slap fingerprints are 4 fingerprints of your left hand, 4 fingerprints of your right hand, and then the 2 thumbprints in the middle. So this is captured under the controlled conditions. But what about at the crime scene? At the crime scene, you have a partial noisy fingerprint, which is often referred to as the latent prints. So when we want to know whether this person has committed a crime before or he is in a criminal database, we do 10 print to 10 print comparison, which is a fairly straightforward problem in the sense that accuracy is almost 99.9% or so. The crime scene evidence, taking a partial fingerprint and trying to find out who left the partial fingerprint at the crime scene, that's a very challenging problem. And that accuracy is only about 70%. So the first criminal case where a person was arrested based on fingerprint evidence was reported by Scott 5. And the United States Congress authorized the FBI to start collecting fingerprints almost 100 years ago in 1924. Next slide. So since early applications in forensics and law enforcement, there are a large number of applications. Our supermarket, where I live in Michigan, the cashiers all have a fingerprint. And India's Aadhaar system, which has about 1.5 billion enrollment. That is, there are 1.5 billion people in the database. And at the transaction time, your fingerprints and your 12-digit ID number are provided. And then the answer comes back from the server, yes or no. That is, this fingerprint provided actually is linked to that 12-digit ID number. The Federal Credit Union in our town, the officers all have fingerprints to access different databases. And in Disney Park, all the Disney parks have a fingerprint reader where you scan your badge and then it gets authenticated. That fingerprint is linked to that badge so that nobody else can use that badge. So this avoids the sharing of the ticket among multiple peoples. Next slide. At the immigration, I'm sure you're familiar with the Hong Kong immigration. This is Incheon Airport in Seoul, where the fingerprints are used. Mexico immigration is using the slab scanners to capture the fingerprints. And then the handheld terminals are used to capture fingerprints of refugees as well as those who cross the border to the US illegally. Next slide. The technology is the enabler for the application of fingerprints. As I mentioned, this is the Apple Touch ID in 2013. And then in 2018, under the display, fingerprint readers were introduced. So why was this under the in-display reader was introduced? Because the mobile companies wanted to get rid of the bezel around the screen and increase the screen size. So if you want to increase the screen size, there was no home button left to put the fingerprint reader. So Apple couldn't perfect the technology for the in-display reader and went with the face recognition, 3D face recognition, whereas all the other phone manufacturers decided to stick with the fingerprint reader. And now, just recently, the smart credit cards have been introduced where the fingerprint reader is also embedded in the card. So this technology is referred to as match on card. The sensor, fingerprint reader, feature extractor, and matcher, everything resides on the card. So your fingerprint actually never leaves, is always in your possession. And that's where the security comes in and the users are going to be more comfortable. This technology is in early stages. It's not clear yet what will be the longevity of such smart cards, how much it will cost, and who will pay for the card and the replacement cards. But this is really getting to the future of where fingerprint technology is going. Next slide. So now I want to talk about two scenarios for fingerprint recognition. One is called authentication, one-to-one comparison. I provide my fingerprint and I claim I'm Anil Jain. The system will search the database for Anil Jain's fingerprint, which is already enrolled, and then answer the question, are these two impressions made by Anil Jain? So this is where the authentication takes place. You claim who you are, you provide your fingerprint, and then it is determined whether this fingerprint matches Anil Jain's fingerprint in the database. This is a relatively simpler problem. The more challenging problem is one-to-N comparison. So we go to the next slide. So we have a query, and can you click on it? Yeah. You have a query and it is searched against a database to determine whether there is a matching fingerprint or fingerprint with sufficient similarity in the database. So basically here, you don't make a claim who you are, or we don't trust the claim you're making. We simply take the image and we search the entire database. Remember, in the authentication, you claimed who you are, so we only compared your query image with who you claim to be. But here, we have to search your fingerprint with everybody in the database. So this is a more challenging problem, especially as the size of the database, a number of enrolled users starts increasing. So in Hong Kong, there are about 10 million residents. So N is 10 million. In FBI database, the size of the database about 150 million enrollments. And India's Aadhaar database is 1.5 billion enrollment. So you can imagine matching a query to 1.5 billion database is rather challenging. So that's why in India's Aadhaar program, we use all 10 fingerprints, we use face image and 2 iris images to do what is called the deduplication, that is making a distinction among the 1.5 billion population. Next slide, please. So how was fingerprint matching done before the computers were there? I visited this center in 1970s, the Michigan State Police Bureau of Fingerprinting. So the first automated fingerprint matching systems, or AFIS, didn't come until early 1980s. And this is the picture is dated 1960. So there are filing cabinets where all the fingerprints were filed according to what type they are: left loop, right loop, whorl, arch, dented arch. And then when a new fingerprint or a query came in, they would sort of go to the appropriate filing cabinet and pull it out, and then manually using a magnifying glass determine a match. That's a very tedious process. Of course, we didn't have as many criminals in 1960s and 70s, so the size of the FBI database is 150 million now. In 1960, it was maybe hundreds of thousands. But still, it was a very tedious job. The next slide, please. And then the computers came. So the AFIS, Automated Fingerprint Identification System. So next, the first slide on the left, the image on the left, Michigan State Police, that's their 1989 Automated Fingerprint Identification System. And you can imagine the computer technology in 1980s. And this system occupied the whole room. And you can tell from the size of the monitors, the CRTs, what the technology was. And now, in 2018 and subsequently, the system occupies only a much powerful system occupies only a small part of the room. So the technology is what's really driving the use of fingerprint in a variety of applications. Next slide, please. So they had the modules of a fingerprint identification system. So in the green, I'm showing the enrollment. So before, you have to be in a database before fingerprints or face or iris can be used. So enrollment means your fingerprints are taken along with your ID information. The pre-processing simply means image enhancement, cropping, alignment, which are standard operations. And then we extract some features from the image. And those features form what is referred to as the template, and it is stored in a database. Often it's called enrollment database or template database. When we want to recognize somebody, the person provides the fingerprint, that's referred to as the query. It goes through the same process, similar pre-processing, same feature extractor. And now we have a matcher which compares the image, the query image, with the database image. If you know who you are, if you claim who you are, then only one image is pulled from the template database. If you don't claim who you are, then the query is matched to every image in the database. A threshold is specified for the similarity between the two fingerprint images. The fingerprint matching by itself doesn't say whether it matches or not. It only computes a similarity between the two images, a query image and a database image. You have to specify a threshold, and then the system determines whether your similarity exceeds the threshold or does not exceed the threshold. Next slide, please. So now the basic challenges in all machine learning AI is what features to extract. And there are two distinct ways of doing this. One is we use the expert knowledge, often referred to as handcrafted features, and use that to learn some decision boundary and then do the prediction. The modern version, or the deep network version, is you feed in huge amount of data to a network, which is referred to as convolution neural network in image processing. And this network learns what should be the right representation to distinguish among different fingerprint classes. And then you do the prediction based on the features it has learned. Both the approaches have advantages and disadvantages. And as I will show later, it's the combination of the two approaches, which in our case in fingerprint recognition definitely improves the performance. So first, let's talk about the handcrafted features which have been used for 100 years in fingerprint, and they are still used. So let's talk about that in the next slide. So given a fingerprint, there are 3 levels of features we can extract. At the lowest level, which gives you the gross characteristics, what is referred to as the ridge flow, how the ridges are flowing, that's referred to as level 1. And it determines what type of fingerprint it is. Type of the fingerprint, arch, loop, whorl. In fact, if you look closely at your fingerprints, you will notice that you can tell whether the ridges are flowing from left to right, right to left, whether there is a double loop that is both left and the right loop, also referred to as the whorl, or whether it is an arch or a tented arch. In fact, there was a guy, Henry system of classification, which identified 17 different types. But I would say about 99% of the fingerprints belong to arch, tented arch, left loop, right loop, and double loop. So level 1 features are primarily telling you the type of the fingerprint, and level 2 features establish the correspondence between the 2 fingerprint images, and that establishes the matching score. Level 3 features are highly detailed, which most commercial AFIS systems do not use. Perhaps the manual forensic examiners use it to fine-tune the decisions made by the AFIS, because these are noisy features which are very difficult to reliably extract. Next slide, please. So I want to show how the matching works based on the minutiae. And I think you'll have to use the cursor to move it's an animation. So if you click it again, you will. Yes. So we have a query fingerprint and enroll fingerprint. In the next set of images, you will see the minutiae point. If you click again, please. So here it is doing thinning and finding the ridges, and the minutiae points are where the ridges bifurcate or the ridges end. So if you click again, you will see the minutiae points, and now we have established a correspondence or point matching, and we get a similarity score. In fact, 30 years ago, when we started on this project with FPGA, this is the problem we proposed. Given 2 sets of points, how do we do the correspondence? And 30 years ago, we showed that we could, using this FPGA technology, we could do this point correspondence 100 times faster than a CPU processor. And so that was our contribution, and that led us to continue working on this problem. Next slide, please. So now we know the whole job in machine learning, AI, face recognition is to find a similarity between 2 objects, 2 images. And now we look at the similarity score distributions in the case of fingerprint. So there are 2 distributions, imposter distribution and genuine distribution. Genuine distribution means I compare my fingerprint captured many, many times. And ideally, it should always be the same, but it's never the same because of the amount of pressure I apply on the reader, the condition of the finger, humidity, dryness, and so on, whether I provided a partial fingerprint. So the genuine distribution has a finite variance. Imposter distribution also has a finite variance, although imposter distribution is generally has a smaller variance than the genuine distribution. And because these 2 distributions overlap, no matter where you choose the threshold, we will have 2 types of errors: false accept and false. Sorry, if you go back, sorry. Yeah, false accept and false reject. So you have to choose your threshold based on which error you want to specify. You cannot simultaneously, for a given representation, for a given set of features, we cannot simultaneously reduce both of them. So typically we choose a threshold which satisfies a given false accept rate. And typically false accept rate, which is used in fingerprint recognition, is 0.01%, which is 1 in 10,000. So that is in 1 in 10,000 cases, I will accept PC as Anil Jain. My fingerprint recognition system will accept PC's fingerprint as Anil Jain's fingerprint. So this is very important to understand because same fingerprint recognition system could be used in different applications and it could be operating at different false accept rates. Okay, next slide, please. So what is the state of the art in fingerprint recognition? The true accept rate for rolled prints and plain prints is 99.96% at a false accept rate of 0.01%. And these numbers come from a third-party evaluations, primarily NIST evaluations, and also from the fingerprint verification competition run by University of Bologna. What about the search accuracy? Rank 1 retrieval, that is the top retrieval from a database of 5 million, is 99.9%. Latent print search accuracy, which is the partial and noisy fingerprint, that is only about 70%. So it's clear that if the fingerprint quality is good, accuracy is very high, but if the fingerprint quality is poor, accuracy is low. But even in search accuracy for n equal to 5 million of 99.9% is not really acceptable as you start increasing n to 100 million, 500 million, or a billion. And I think that's the important thing to note in fingerprint recognition. You cannot stop at 99.9% accuracy. You have to keep pushing it further. Because what happens if you make a wrong mistake, it could lead to serious issues if I'm not retrieved properly or I'm incorrectly retrieved from a database of criminals. And that's what I want to show you in the next slide. Wrongful apprehension because of the false match by a fingerprint recognition system. So this case happened in 2004. In 2004, there was a tragic incident at the Madrid train station. There was a bombing. A lot of innocent people were killed. And these Spanish police found a duffel bag with a partial smudgy fingerprint, which is shown on the left. And it sent this print to the FBI, and FBI used its AFIS system, and it found a match with the fingerprint in the database shown in the right. And this fingerprint on the right belongs to Brendan Mayfield, who was a captain in the US Army. And all the Army personnel's fingerprints are in the database, not because they committed the crime, but their fingerprints are there. And typically, a forensic expert is supposed to evaluate this match, but apparently that procedure was not followed, and the FBI agents went to Brandon Mayfield's house, who lived in Oregon, and said, well, this is what happened. And Brandon Mayfield said, well, I never left the state. I was always in the United States. And the police, FBI said, well, fingerprints do not lie. And they put him in jail for 2 weeks. And then later on, the correct suspect was found, criminal was found. And so this led to a lot of investigation. The point here is we rely so much on fingerprints in terms of border crossing, in terms of arresting criminals, in terms of payment systems, in terms of which can involve a lot of fraud. So if the system is not, if we cannot keep on increasing the accuracy of the system, the public will lose trust in the system. Next slide, please. So then the path forward, there are 3 things which are very important. Scalability, how do we scale up the system? Accuracy, how do we keep on increasing the accuracy of the system? And thirdly, acquisition. Are we obtaining fingerprints in constrained environment or unconstrained environment? So constrained environment is when you are sitting in front of an officer providing your fingerprints. Unconstrained is the fingerprints which you find at a crime scene. In addition, we also want to make sure that the fingerprints which the people provide at the enrollment, they are secure, they are protected. How does the technology affect the future performance of the fingerprint recognition? Sensing technology keeps on changing. How do we have sensor interoperability? And how do we do the speed of the system? If searching against 100 million database is going to take several hours, that's not acceptable. So I think that those are the issues which I want to emphasize, but I'm limited time, so if we can move a little bit fast, please. Next slide. So this shows you problems with fingerprint recognition. We use our hand to do a lot of work. We do decoration. Henna is very popular in India, in Middle East, and especially during certain festival seasons. And doing any recognition based on this is just not possible. This also shows the limitations of a fingerprint. In the bottom row, I'm showing you 3 fingerprint images. One is of very good quality. If you can provide always a fingerprint of this quality, accuracy will be 99.9999%. But the fingerprints of marginal quality or relatively poor quality will have problems. Next slide, please. So now I want to talk about the second type of features where we have made significant contributions in the last few years. So I've already talked to you about the handcrafted features, the minutiae points from fingerprints. What about if we just use a trained network and learn the features from the fingerprints without any preconception about what type of features we want? And this is what we have been focusing on. But in order to train a deep network to learn some features, we need huge amounts of data. And fortunately, we have access to this large amount of data through our contact with the Michigan State Police. And what we have been able to do is to obtain a 192-dimensional fixed length representation for the fingerprints. And what is the advantage of that? The matching is extremely fast. Comparing 292-dimensional vectors using a cosine distance, which is what is used in face recognition, it's about 3 to 4 times faster than minutiae matching, which are arbitrary number, and you have to use some kind of a graph correspondence to do the matching. In fact, we have shown that comparing this, our deep network learned features, they can do 10 million comparisons per second on an Intel i9 processor. And that's exactly the reason why NEC licensed this algorithm, and we were issued a patent for this vector. Next slide, please. So one of the reasons why this network learned features in combination with the handcrafted features are important is because if we have 100 million gallery, 100 million users enrolled in a database, I can first use the query image, use the deep print to find the top K candidates. And then we use the proprietary minutiae based features to resort the list. And that, so in order for this to work, the learned features, which our system is called as deep print, has to be extremely accurate, almost with the same accuracy as the minutiae-based features. And this is exactly what we have. Our deep print features are almost as accurate as the minutiae-based features, but they are extremely fast. So we are combining the strengths of the two representations to achieve a significantly better result. Next slide, please. So now the question is, we are fortunate to have this large database of fingerprints to train a network. But you know, the data is becoming very difficult to get. This is true for face recognition as well as for fingerprint recognition. The largest database we have for fingerprints is for 2,000 unique fingers and 25,000 images. That's not enough to train a complex network. So what we wanted to do was to see if we can generate synthetic fingerprints which have the same characteristics as the real fingerprints. And this we have been able to do, and we have shown that with data augmentation with synthetic images improves the model, leads to a better model with improved performance. And this has also been licensed by NEC. And since then, we have also worked on another problem of synthesizing latent fingerprints, which are even in shorter supply. And that also is being licensed by NEC. Next slide, please. So I want to show you that these images, synthetic images, are really difficult to tell apart. So I have a panel here of 8 images, which one says real, which one is synthetic. And if you click again on it, you will see. Can you please click on the slide? Go to the next slide. The ones shown in green are the real images and the others are synthetic images. Next slide, please. Same thing, another challenge is these are fingerprint images made of different materials, and I can take your fingerprint and make a spoof and carry your fingerprint in my pocket. So that means we need a method to detect whether the fingerprint is real or bona fide or a spoof is also referred to as the presentation attack. Next slide. And you know, so we have to look at what characteristics are present which makes a fingerprint different, spoof fingerprint different from the real. And it's surprisingly, it's very difficult. So if you click again, you will see in the green is the real fingerprint and the others are made from one of these synthetic materials. So we have developed an algorithm which is state of the art in telling whether the fingerprint presented is bona fide or spoof. Next slide, please. And finally, I would like to mention about this fingerprint alteration. Spoof is one type of attack where you adopt somebody else's identity. In fingerprint alteration, you evade your identity. That is, you don't want to be identified. And as early as 1933, a person named Winkler changed his fingerprint. So the type of the fingerprint, instead of double loop, it became the left loop. So if he had a criminal record and he comes to the system, he won't be recognized. And this technology, which we developed a few years back, was licensed to Morpho, which is now known as the IDEMIA. Next slide, please. And this, if you saw the movie Men in Black, this technology or this approach of deleting your fingertips was shown by Will Smith in this movie. Next slide. I think let's just skip this and move to the next slide. And so in summary, with over 100 years of success in forensics and law enforcement, fingerprint recognition is now mainstream. We use it in access control, mobile unlock, immigration, and benefits distribution. Fingerprint recognition is not a solved problem. Unlike other AI ML problems, it has unique requirements. First of all, the huge number of distinct and dynamic classes. The current world population just exceeded 8 billion. So in a sense, we have an 8 billion class problem, which is dynamic because, you know, there are about 130 million new births every year. So the number of classes is increasing every year. We require an extremely high accuracy, and no accuracy is enough. We have to keep on pushing it as the size of the database continues to increase. We need a fast prediction. The system has to be usable, and we need to maintain the user privacy and system security. And that is why authentication systems like match on card or mobile phone unlock and mobile phone payment are extremely desirable, because there is no centralized database of fingerprints in those applications. Your fingerprints resides either in your mobile phone or in the card, which are not so easy to compromise as a central database. So with that, I will stop. I'm just very fortunate to be working in this area of fingerprint recognition for the past 30 years. And I've also been privileged to work with a large number of students and postdocs who continue to be in my lab and who continue to make contributions. Every time a student graduates, I wonder what will be the next problem. But somehow or the other, we figure out what the next frontier is in fingerprint, and we continue to embark on that. So thank you very much for your attention, and I'll be happy to answer any questions which you may have.
Thank you very much. Thank you very much, Prof. Jain, for giving such a very inspiring and wonderful talk. Okay, may I invite questions from the floor? Questions? Yes, please.
Hi, dear. Hi, dear Professor. Thanks very much for your interesting talks. So I think my first question is that I think in your presentation and in your talk, you mainly focus on the fingerprint recognition. But I am interested in, I am more interested in the privacy issues. Yeah. In general, I know that we can use something like the data hiding or digital watermarking to preserve, the user privacy of such kinds of biometric data. But we can also find many privacy leakage issues nowadays. So my question is that, how can we find, do we have better solution beyond the digital watermarking or the data hiding frameworks nowadays to better preserve the privacy issues?
So the slide I did not cover is the question you asked. So if you can go to the last but one slide of my presentation, please. The last slide. Yeah, the number 36. Yes, can you, yes. So this shows, so there has been a lot of work going on matching in encrypted domain. And I think the technology is here. The solutions are here. So in this picture, I'm showing you, we have a fingerprint reader. The reader itself does the encryption. So the image which comes out of the reader is an encrypted query. The database images or enrolled database images are all encrypted. And typically, when you do the matching between the query and the database images, you have to decrypt the images and then do the matching. But there are now techniques, something called homomorphic encryption, which allows you to do the matching in the encrypted domain. And there are some theoretical guarantees available that this is extremely secure. And we have also shown, and the citation below in the slide shows this shows that there is no loss in accuracy, or if there is one, it is due to the arithmetic rounding errors. And this is secure. I think the issue becomes when you're doing a very large number of matching. So in 1-to-n matching, where n may be several millions, that there may be a little bit of latency introduced. But otherwise, this kind of an approach is something which is gaining a lot of attention. So in this scenario, it is extremely difficult to get hold of the image. Hope this answers your question.
Okay, thanks very much. And I also have another question. Okay, can I ask? So my second question is, in your summary, you say that the fingerprint recognition is now the mainstream, but we can still find that many mobile manufacturers, I mean the mobile phone manufacturers, they may adopt some other, I mean the biometric verification systems like the face recognition.
Yes. Sure.
Okay.
Sure. I think it's fingerprint. You'll be surprised to know that in mobile phone, the whole fingerprint recognition module, hardware, the matcher, everything, cost on less than $1. Okay.
Okay.
Face recognition costs about $5.
Okay.
So so everybody, the only company I know which makes face recognition for mobile is Apple, and Apple is also considering moving to some other modality which may be cheaper. So the cost of the mobile phone is a big factor in marketing for a large population. Not everybody can afford $1,000 mobile. So yeah, I will stop at this point, and maybe if there are others who have questions, we can take that.
Okay. Thanks very much.
Yeah.
Okay, and my third question is that.
No. Can we move on to somebody else?
Other participants have chance. Okay, maybe we can entertain one more question on the floor before we move to the question from online participants. Any question from the floor? If no, then let's move to the questions from online.
So there's a question: why are the thumbs scanned twice? Once in row 1 and 2, and once in the third row.
Right.
So basically, you are taking. There are two different methods of fingerprint acquisition. One is called rolled. Have you ever had your fingerprints taken? Well, the rolled prints in the Hong Kong ID card, I believe they roll your fingerprint, or is it just a slap fingerprint? PC, do you remember?
I'm not sure. I think it's
okay. So the first two rows show the 5 fingers from one hand and 5 fingers from the second hand. So the row 1 shows 5 fingers from left hand. Row 2 shows 5 fingers from the second hand. So there's a left thumb, there's a right thumb. In the last row, it is called slap, where you simply touch your 4 fingers on a glass of the reader, and then you touch your second hand's 4 fingers on the glass platen, and then you put your left and right thumbs together on the glass platen. Okay, so it's the different methods of acquisition. One is rolled, other is slap. And it turns out that rolled is more accurate because it covers more surface area of the friction bridges, but its time to capture is much larger, whereas slap is much faster, but of course it covers slightly lower area. So hope that answers your question.
Okay.
Then there's a
question, yeah, from Timothy. Yeah.
Okay, go ahead. There's a next question: is it time, place, RAM consuming for pinpoint machine in early era to translate human fingerprint as useful digits for analysis? I'm not sure if I understand what this means. What does
Timothy, you want to ask the question directly to Prof. Jain? We can unmute. Yeah.
Then there's a question from Hu Han.
Yeah, another question from ICT. Yeah, from China.
Yes, about when such technologies are being widely used in our daily lives, adversarial sample generation technologies have achieved a great progress in recent years. Can you comment how we can effectively perform fingerprint anti-spoofing for such kind of adversarial fingerprint images in unattended fingerprint identification systems? Yes, that's a very good question, Hu. And I think so far, most of the fingerprint identification systems are in attended mode. And in order to, there have been some investigations about the, digital, instead of physical spoof, digital spoofs. But I'm not, I mean, from academic research perspective, it is fine. But I think from the practical scenario, at least I have not been able to come up with some use cases for such research in fingerprint scenario. I mean, how to inject an adversarial image into the closed loop fingerprint recognition system. That is something, perhaps you and I can talk about it offline and see if there is I'm missing something here. Short for by, is there anything that could not be done by deep learning? Well, deep learning, everything can be done by deep learning, but the question is, how much importance do we have of domain knowledge? I mean, most of the audience is too young to remember what the role of eigenvectors and principal component analysis. So they were used for face recognition, eigenface. You remember PC, eigenface?
Yeah.
Okay. And then this eigenvector idea was applied to everything. Eigengate, eigeniris, everything can be done with using this principal component space. So I think the same thing is true for deep learning. Everything can be done with deep learning. The question is, there is a limit to how much you can learn with deep learning and how much data you can access to train the network. At some point, the domain knowledge becomes extremely important as well. And that's what I hope I showed a little bit, that a combination of both the domain knowledge and network learning can give you that extra mile which you need in a variety of high accuracy applications.
Okay,
Okay.
Firstly, I think we missed one question online. So can I read
Okay.
for you?
I think there is a do fingerprints change significantly with age? If so, how often would you need to re-fingerprint somebody to preserve accuracy? Well, that's a good question. I think in India's Aadhaar program, for example, which has been around for 12 years now, first of all, they don't start the enrollment till you're 5 years old. And then when you enroll at 5, then they re-enroll you at the age of 15. And but after that, they don't re-enroll you. And I think but there can be problems. For example, if the weather is very cold and as you age, the fingerprints start showing some wrinkles, and in some cases it can cause problems. But more problem is caused by the occupational reasons. So, for example, in India, in the villages where people do a lot of manual work, the farmers or construction workers, they have problem getting recognized by fingerprints. So there's always this backup finger. I mean, you have one primary finger. If it doesn't work, then you use the second finger. And If that doesn't work, they have started now face recognition as another alternative to, because re-enrollment is also not an easy task. It requires a lot of resources. So I think relying on another modality like face may be an alternative. Okay, what is the other question?
Okay,
What is the advantage of fingerprint recognition compared to palm print recognition? Why palm print recognition is not that popular? Well, Amazon has started using palm print recognition, and typically palm print scanners are bigger than fingerprint scanners. They cost more, and the computational resources required to match palm prints is much more. So for example, in a fingerprint, suppose you have 100 minutia points at the most, palm print can have 1,000 minutia points. So matching 1,000 minutia points, an order of magnitude larger than fingerprints, would require a lot more computational resources.
Okay, Sunny, it's your turn. It's your turn.
Thank you very much. Thank you very much. Can you hear me, right?
Yes.
Okay, well, first of all, thank you very much for such a wonderful presentation, Professor Jain. It is good to know all this latest and greatest development of a fingerprint recognitions, especially that actually people in your field are pushing for the high accuracy. So one question I do have is, I'm wondering that actually how the surface scratches on the fingerprint reader itself may potentially affect the matching accuracy, especially when the ongoing learning function is on, when you're doing the one-to-one authentications.
Yes, so I mean ultimately, no matter which application of imaging you are doing, if the image quality is poor, even in your mobile phone camera, if it is dirty, the pictures won't come out very good, right? And if you're going to do recognition based on that, that's a problem. So typically fingerprint recognition surfaces, or just like your mobile, which has a fingerprint reader, if the surface of if the home button is dirty, or your finger is oily or very dry, you will have the same problem. So the fingerprint reader surfaces need to be cleaned if after repeated usage, because some residual prints may be left behind, and or somebody may maliciously scratch the surface of the fingerprint reader, so fingerprint reader as a security mechanism doesn't work, right? So
exactly, yes.
This is like another kind of an attack on the fingerprint recognition system.
Right.
So yeah, you may just paint it all black, it doesn't work. So yes, so one has to be, of course, look out for such thing. And it's like, you have a CCTV camera, you can simply cover it or spray something on it. Now there's no surveillance mechanism. So yes, so these are sort of larger system issues which we always have to address. One could simply shut off the power, right? And then the devices don't work. So yes, in the broader sense of security, just having a fingerprint recognition system doesn't solve everything, right? It's only a small part of the overall security.
Yes, the reasons why I bring this up is because in reality, even though that actually from the algorithm standpoint, I think that the people, the talent in your field are pushing for extremely high accuracy. However, the reality is actually when you come to the real scenario usage, it is very difficult from the practicality standpoint to guarantee a good quality fingerprint. And one challenge that I know that cell phone makers, the CMOS imaging sensor guys are facing is basically the scratches on the interface glass. And especially when the machine learning actually turns on, right? Just for example, say in the one-to-one authentications, the fingerprint, for example, say the fingerprint on your cell phone. And because the machine itself, the device itself is keep on learning the new, every time you actually push your fingerprint on the screen. And every time that they will pick up new signals. And if the screen scratches is building up, and then they will actually start to pick up the scratches as your fingerprint as well. And you know that those scratches on the screen basically will stay there. And so every single time that actually, you have scratches on it, and then the scratches actually keep on building up. And anyone,
right. So,
to the point that to anyone.
Yeah, so there has to be a mechanism to determine the system integrity, okay? You cannot rely that the screen is going to be perfect or the sensor is always going to be perfect. So you need to have a overall system integrity checks made, okay? And we are, there are other applications where in palm print where we are encountering this. What if somebody maliciously, mobile phone is your own device, so of course, doesn't mean you cannot maliciously, you may be upset one day and just scratch the surface, but in a public access control system, this problem can also occur. And there is always this danger of continuously learning without regard to the quality of the image. You cannot just update, have a continuously learning, machine learning system and not pay attention to the quality of the image.
Yep. Basically, otherwise, garbage in, garbage out. Okay. Well,
exactly.
Thank you very much for your answer. Thanks.
I think because there's still some question online. Because of time, maybe we can entertain the last questions. And then, I believe that you still continue answering the question through emails. Okay.
Yes, definitely.
Invite Tiffany to ask the last question.
Is that the question? Is there any explanation for the match result of fingerprint? Why should we trust the prediction? Is that the
no? I think Timothy, are you here? Okay, then we can. The next question is there an explanation for the matching result of fingerprint?
Yes. Yeah, that's a very good question. When you use a human or expert driven or handcrafted features, then there is an explanation. A human expert can go to the court and say, these two fingerprints match because, so many points from the query image match so many points in the database image, and when I align them, I can see that the ridges overlap. Okay, so that's one could give an explanation like that, and that's the kind of explanations which are given. But when you have a deep network, it is very difficult. And so just imagine somebody, John, is convicted of a crime, and the defense brings one deep network which says, well, the score is very low, and the prosecution brings another deep network which says the score is very high. And now how do we resolve this? So that's why this notion of explainability, some graphical representation, visualization is being studied, but there is no hard answer right now which I can offer you when you use strictly a deep network for trusting the prediction.
Okay, thank you very much.
Thanks.
Before the end of the lecture, let's have a group photo taking. So we just follow the instruction from Maisie. Okay, thank you very much.